Thank you very much for the invitation and all that, and I hope you don't mind if I speak in English. I'll try to speak slowly, but it's not my strength. As you see, this is a joint action by many people in my group, and before I start, I'd like to thank all the people who paid for it. But you probably don't care about that. You probably want to know what the expensive brain is about. And in fact, you already heard quite a bit of it from Jean-Jacques. But our group, we try to understand human evolution based on broad principles that apply everywhere, and then conditions that are specific to our evolution to explain this. So no magic, no special things that only apply to humans. And of course, as you know, and that's basically one of the big problems, is that over the last 2 million years, roughly, the brain of hominins, including our ancestors, have been increasing roughly threefold beyond that range, that dotted lines that you see below, which is the range of the great apes, the current extant great apes. And a valid question is, why and how could that happen? And Jean-Jacques already gave the answer. We think energy has a lot to do with it, calories. So I could stop here, but you probably want to know more than that. So when you have a trait that keeps on increasing rather dramatically for such a long time, you have to figure out, okay, what causes an increase in a trait? What causes selection to do that? And of course, as always, there's costs and benefits. So normally we ignore these costs. But as Jean-Jacques already pointed out, you can't do that in the case of brains. So if you look at the fitness cost of the increase in brain size, they're quite appreciable. Because, as Jean-Jacques already pointed out, brains are among the most expensive tissues in our body, and also quite variable in size. And so, oh God, that's very interesting. I hope it doesn't come back. I don't have to get out of the presentation otherwise. But basically compared to guts that were already mentioned, or lungs, or skeletal muscle, or skin, or bones, brains are much more expensive and quite variable in size across species. And of course, when you sleep, or when you're awake, it roughly uses the same amount of energy. This is perhaps the most important part about brains, because it also means that it's spared as the... Oh God, sorry, I have to get out of this thing for a second, if I can, and turn this damn thing off. So, let me get back in. All right, and where was I? Right, brains are expensive at all times. And as a result, for instance, if you starve adult people, don't ask where the data come from. You know, they lose all their fat, they lose all kinds of other things, and the brain with the little circle stays roughly where it is. So brains are so expensive that you could imagine that having increased brain size relative to an ancestral state, if you push the brain up, it's going to affect all kinds of other processes. That's the trade-offs we were talking about earlier. But then, of course, there have to be compensatory benefits if selection ever wants to favor an increase in brain size relative to the ancestral state. And what are these benefits? It's interesting. Of course, they should then maybe improve survival or reproduction. Otherwise, you can't speak of an increase in fitness. What are those benefits? Interestingly, this is primates, but it's probably true for all mammals and birds. What we find is if we take all kinds of cognitive tests that have ever been done in a way that you can compare species, so it's the same test, multiple species done, you can rank them. If you do the analysis, what you find is that you can sort of sort all that variation on one axis. We called it their global cognition. Now we think it's the same thing as what we call in humans general intelligence. And you see it's really tightly linked to brain size. One of the reasons to think it is something like general intelligence is because if you look at self-control or inhibitory control, which is one of the best predictors for intelligence in humans, across species, these are just overlapping data sets, you see the same very nice pattern, just like in humans. So basically the evolution of brain size, at least in primates and probably lots of other lineages, is the evolution of intelligence. And intelligence is all about flexibility. It's about solving problems. And so you would predict that that should be good for survival and reproduction. Why would we be here otherwise? Let's try and get a handle on this by comparing patterns across species, because there should be predictable patterns across species. And I'll give you the results just for precocial mammals. We've done a lot of work on all kinds of groups. And what you see, if you ask the first question here, and these graphs are for illustration, they're always showing residuals, which means you've corrected for body mass. So on the x-axis, you've got brain mass. On the y-axis here, you've got maximum lifespan. And you see there's a positive correlation. It's highly significant. Of course, if you throw in lots of species, you'll get that. It's all corrected for phylogenetic non-independence, as they call it. But what you see, in other words, is that if selection, if survival is increased systematically, then over time, selection will change life history so that there's a design to live longer, and therefore, you're going to measure that. You pick up that in maximum lifespan. That's what you see here. So that's good. What you don't see is an increase in reproduction. In fact, you see the opposite. Now we know that there's a lot to do with the fact that larger brain species tend to have much larger offspring and fatter offspring in general, as I'm sure other people will talk about, Chris maybe. And so that doesn't seem to work. So these benefits are actually not as nice as you might think. Yes, you get more survival, but you don't get more reproduction from a larger brain. We can do the same thing, of course, for the energy cost side of things. Again, looking at the same set of precocial mammals. What you do see is a very strong effect on maturation time. In other words, if you have a larger brain, it takes you much longer to grow up. You know, if you're human, you understand what I'm talking about. And so that is a clear fitness cost to having a larger brain. And of course, that fertility thing doesn't change. So basically, yes, you have increased survival, but not increased reproduction, reduced reproduction, and slower development. But maybe there's other things that are also trading off. It was mentioned, basically the publication that got us all going on this whole set of questions, Ayala Wheeler. We tested it a couple of years ago. It was mentioned by Jean-Jacques. And we found a significant correlation, but in the wrong direction, opposite. And so at least the gut-brain trade-off idea is out. There may be other trade-offs that are still relevant. So that one's gone. So basically, you look at a picture here that says, well, it's going to be hard for brains to increase, right? So basically, if selection on brain size is going to be positive, the fitness gains, which is basically improved survival, have to outweigh the fitness loss component due to slowdown in development and reproduction. And so the question is, what conditions can make this balance positive? And I thought a long time about this, and basically you can come up with three possible pathways. The one that says one is that there may be variability in how well being smarter translates into increased survival. There may be unavoidable starvation, unavoidable predation that no matter how clever you are, you can't deal with. The second one is arrow number 2, which would be worth a whole lecture in itself, because these cognitive benefits, there are skills that need to be constructed during development that take time. How efficient that process is, how many and how good the inputs are in the developmental process to construct these skills in a brain may vary quite a bit. And for instance, if you start teaching, that may become much more efficient. And so with the same amount of brain, you might get more survival and fitness. But there's also this third pathway, which is the one that I'm going to talk about today, and it's most relevant to today's topic. And that is, what if cognition, if the skills you have there with this increased brain actually generate the energy and in the best possible case, pay for the brain itself, so that this whole yellow box with development and reproduction just disappears. And that's what I'm going to focus on today. So if you think about it, think of the energy budget as a cake. I like to eat. And so the gray part there is the slice of the cake that goes to the brain. The blue part is that goes to the rest of the body. What we've looked at so far is the trade-off issue. So, well, if you slice, you cut a bigger slice to the brain, something has to give. But of course, there's also the possibility that you actually make the cake bigger. So you have more energy coming in and going through the organism, with the emphasis, of course, having to be on stability, because as we saw with the brain sparing, the brain cannot go hungry for some time. It always has to get its full share of the energy that it wants. One way to measure that is to look at basal metabolic rate. And I expect a lot more about it from Herman Ponser in his presentation. We looked at it briefly, and we saw in primates that there's a nice correlation there, again, between brain size and the basal metabolic rate. It's actually quite a nice correlation, but it really holds most strongly in primates. Outside of primates, it's not very strong. The correlation, though, between basal metabolic rate as a proxy of total energy expenditure, that DEE, daily energy expenditure, is actually not so strong, and it still doesn't tell us what mechanism we're talking about, so we have to be more specific than that. This is not the end of the story. So there's three ways we can imagine a stable increase in energy input. One is somebody gives you the energy. Allomaternal inputs. Humans are cooperative breeders, so it's a relevant question for humans as well. So we thought about it. We did some papers on it earlier, but we thought about it some more because, again, think of that stability issue. It has to be there at all times. If you look at allomaternal inputs, so inputs from others than the mother, they can come from the male. He's always there. If he's not there, there's no reproduction. But it can also come from the other helpers, but that number is fluctuating over time. So selection is probably not going to make that very strongly, putting that energy into the brain. It's more likely that that's going to be put in fertility. So that would be our prediction. And now that we test this recently on about 500 species of mammals, we see that the male care brain size correlation is significant. The one by helpers is close. We have a very serious collinearity problem, so we're doing all kinds of variable models and so on. But the good thing is that the fertility link is very, very strong with the helpers and not with the male. So the differentiation we made there seems to work. So yes, if you get energy subsidies, you can increase brain size, especially if you have a male to help you or a reliable number of helpers. How about diet quality? There was a paper last year that looked at that and found something we all knew, but now nicely formalized, that if you eat a lot of leaves as a primate, you have a small brain. In other words, if you have a higher quality diet, you can afford a larger brain. Unfortunately, of course, it doesn't talk about stability, so we really don't know whether this actually does the trick. It may contribute, it cannot be a big part of the story. This, we think, is the big story, is if you can somehow stabilize your energy intake and avoid these troughs, these lean periods that are often there in the environment. And first I'm going to show you that these lean periods really matter, and then what you can do about it. So here is you in an environment. You are red, and what you do is you follow green. So green is what's out there, available as food, and you just follow what's out there. The purple line is what your brain needs, and as you can tell, that's not going to work because you're going to have a period in the middle there where you don't meet your requirements. And so the expensive brain says you have to reduce your requirements. We can test that, of course. So we did look at this experience seasonality here on the y-axis, which is coefficient of variation in the monthly energy intake estimates of primates. And then we look at relative brain size. The prediction would be to be negative. So we looked at 3 different groups of primates, and indeed, it is all the time. So yes, the brain seems to be expensive. If you have a lot of variability in your food intake, your brain's going to be smaller. Recently, we decided to also add these green dots here, which is non-primate mammals, mainly non-carnivorous carnivores and rodents, because for the way we measure these things, you have to look at changes in food composition rather than the amount of food they take in. What we see there is exactly the same result. And so basically, the more your energy intake fluctuates over time, the smaller your brain, just as you would predict based on this whole brain sparing idea. Again, tick. But now, what can you do about it? Well, what you could do about it is now look at the red line here on the right. It's dampened. And one way to dampen that, of course, is by being clever and switching diets or finding clever ways of avoiding destarvation. That's known as the cognitive buffering hypothesis. We can test that too, because now we look at how well you've buffered this by, again, looking at the earlier picture. You can just look at the CV in the red minus the CV in the green, which is what we've done here. And then, again, look at relative brain size, of course, controlling for the experience seasonality. And now we find positive correlations. In other words, if you are good at buffering these environmental fluctuations by reducing the fluctuations in your diet, your brain can get bigger again, or is bigger in general. But notice it's not significant in the prosimian primates. That may be a sample size issue, but there may be also something else going on, because when we then tried, okay, let's look at these non-carnivorous carnivores and rodents, we also don't find it significantly. This graph looks nice, but, oh, sorry, it's the wrong graph, actually. Oops. Well, that's why the graph looks so nice. Excuse me. And so we don't find it in that group. And so this seems to work if you're an anthropoid primate. Not for other mammals so far. So how does it work? How is it done? One of the things you can do is look at how animals get to their food. And so what we did was look at how they eat and how they use their hands for that. And it turns out that it is hierarchically organized. It's a Gutman scale. So for instance, if you're at number 4, you have to do 1, 2, and 3 as well. So it's very hierarchical. And basically, it is about whether you use 1 or 2 hands, with 2 hands being somewhat more complicated, whether your fingers all move at the same time or whether they can move independently, and whether you're dealing with 1 object or 2 objects independently. And if you use that scale, what you see, this is just based on feeding observations, that is beautifully linked to brain size. And of course, here, that little black dot over there, that's us, humans. Suggesting that brains, through their manipulation complexity, can buffer food intake by allowing us to do all kinds of different things with our food. For instance, you can use tools. We also found nearly significant results for extractive foraging. They're cleverer in general. And so what you see is that ways to reduce these fluctuations in energy, to buffer that energy intake against environmental fluctuations, is to first of all start at the high level, get all kinds of good food to begin with, and then be able to switch to alternative foods when they're not available. But most animals can't do that. And so most animals, which we saw, non-anthropoid primates can't do it. They have to put on fat in the bat years, and that's what we see. And so we proxied that by looking at the coefficient of variation in adult body mass, and we validated this. And what you see is the following pattern, that arboreal species show a very strong trade-off between these two things, whereas terrestrial are much more relaxed about it. The overall pattern is all nicely significant and so on. So basically, if we turn these things around, if you cannot buffer by just putting on fat because you're jumping around the trees all the time, think of our ancestors, you're forced to do it in some clever way. It's sort of funny to turn things upside down. We're always so proud of having big brains. Well, it turns out maybe we're forced into that because we have an arboreal ancestry. It also shows that there's sort of complementary strategies. And the extreme case of that, of course, is hibernation. They put on loads and loads of fat, as you can see on the left, and they tend to have much, much smaller brains. So again, that's what you would expect. If you can't deal with it, with these fluctuations, shrink your brain, shrink it quite a bit if you're a hibernator. So, to summarize things, where do we stand here? There's basically these 2 ways of dealing with food scarcity. You can have a big brain, or you can put on a lot of fat seasonally. So it's basically the correlation between the spectrum from cognitive buffering to physiological buffering with hibernation as an extreme case. We also saw this care buffering. In fact, we can show that the species with a lot of allomaternal care put on less fat, and so they're really on that side. Getting help allows you to do this. And if we now, and so basically, as Jean-Jacques already pointed out, and I said in the beginning, it's all about calories. If you want to have a large brain, feed it with calories. And make sure the brain does that for you. Now, running ahead of the story, there's going to be a lot of talks, and just sort of trying to place all these things in perspective a little bit, getting back to this thing. If we look at number 1 again up there, how can you improve survival beyond what's expected? Because we developed weaponry, we could reduce predation risk. Because we developed great technology, including fire, we could certainly reduce starvation risk. We got allomaternal care, which increased survival. We got adult food sharing, which increased survival. And funny enough, we are the only species that are both very big-brained and unusually fat. Terrestrial lifestyle, and so on and so forth. But of course, that improves our survival during periods of scarcity, and we can feed our brain during that period. Now look at number 2. I already said it. We have cooperative breeding and teaching and imitation coming in beyond the ancestral state. And back to number 3, which is what the whole talk was about, is what if you can reduce the energy cost of the brain if it generates its own energy, if it pays for itself in the extreme case, and then all these trade-offs don't occur. And in addition to that, roughly around the time of Homo erectus, apparently we had more efficient locomotion, so that other function trade-off also got reduced. And with that, I know this is a lot of stuff that all of you will talk about in much more detail, but the bottom line remains, it's all about calories. Thank you.